Okay, this is the solutions to the 4A, B, C, and D FIPS for physics. In problem number 1, this is from the 4A, we have 4 people having a tug of war over an object. We have a force of, force of Haley, this direction, 458 newtons. Force of Cayley, this direction, 364 newtons. We are told that we have a force at 35 north of west, which is the force of Shannon, which is 661 newtons, and we are told that we have a force that's at 47 south of east, which is force of Josh, which is 917 newtons. So obviously what we're going to be doing is finding sum of forces on each axis to get a resultant. So sum of forces, we'll go ahead and start with, we'll start with the x-axis. So the only things that we have on the x-axis are the force of Shannon on the x and the force of Josh on the x. Those are going to be this and that. So we'll go ahead and make the force of Shannon a negative and the force of Josh a positive, just using standard Cartesian coordinate systems. So sum of forces on the x is equal to the force of Shannon times the cosine of 35, because for this angle, the portion of the force that's on the x-axis is adjacent to the angle. And for the force of Josh, it would be the force of Josh times the cosine of 47. And remember, we're going to make that a positive number and that a negative number. Okay, once we plug it all in, we get, and I'm not going to go through all the detail here, but we get 83.9329949 newtons, and it's that direction. It's positive because the force of Josh on the x was larger than the force of Shannon on the x. Okay, so now for the y-axis, and this one's actually got 4 forces. So we have the force of Haley, which is up. Well, it's north, I'm sorry, it's north. And we have the force of Shannon on the y, which is also north. We have the force of Cayley, which is south. And we have the force of Josh on the y, which is also south. Okay, so just to use sort of standard conventions, we'll make all of the ones that are heading north positive, and all the ones that are heading south negative. Okay, sum of forces on the y. Well, this is going to be just force of Haley. Force of Shannon on the y is force of Shannon times the sine of 35. Force of Cayley, again, is all on the y, so we don't have to do any trig. And the force of Josh on the y is going to be the force of Josh times the sine of 47. So keeping our conventions about sine in there, oh, and let me draw in the, so there are the forces of Josh on the y and Shannon on the y. So now what we get, and again, I'm not going to put in all the numbers here, I'm not going to go to that level of detail. What we end up with for a sum of forces on the y is negative 197.517 newtons, and that is, of course, south, using our sign conventions. So now we can draw our overall triangle. So if this is our overall triangle, our resultant vector, of course, is going to be that. So this will be our net force. And this is a simple Pythagorean thing. So net force is going to be equal to the square root of 83.9, etc., squared plus negative 197.517, etc., squared. We get a net force of 214.6109, etc., newtons. Now we just have to figure out this angle theta. Okay, so when we look back at our sig figs, this one has 2 sig figs, so this ends up as a net force of 210 newtons. Now to find this angle theta, of course, we're just going to use an inverse tangent, and we get a raw answer of 66.97, etc. So with 2 sig figs, that's going to be 67 degrees, and since we're looking at it in that direction, that's going to be south of east. You could, of course, also take the complement, and that would be 23 degrees east of south. Okay, that's number 1. Okay, number 2, we have someone with an old washer above the head, and, you know, while this might be a good drawing, our free body really, again, just looks like that, except maybe straighter. Okay, so we're told that the combined mass of the person and the object, well, we have a mass of the washer and a mass of Jack in this case. Okay, so sum of forces on the x is 0. We can just walk away from that. What we're looking at is sum of forces on the y. It's 0 because they're not rising into the air or sinking, and that's the force of gravity plus the normal force. They are equal and opposite. They're equal to 0. So we know that the force of gravity, that gravity is exerting back upwards, is equal to the mass of Jack plus the mass of the washer, all times gravity, and that plus Fn must equal 0. And so the gravity of the mass of Jack plus the mass of the washer, gravity times quantity mass of Jack plus mass of the washer, has to be equal to the negative of the normal force. So we have negative 9.81 meters per second squared times 75 kilograms plus 156 kilograms is going to equal the negative of our normal force, and we get negative 2,266.11 newtons is the negative of normal force. So when we do our sig figs, this is going to be 2266.11 newtons equals the normal force, taking out the negative signs. So when considering that we have 2 sig figs, we've got a normal force of 2,300 newtons. That one's pretty easy. Okay, this is number 3 on 4A, and we've got another cable force of tension problem, which everybody just loves. So we have a kid suspended from 2 rings with cables. The angle that these make with the ceiling is 38 degrees. The angles are identical. And we know that we have a force of gravity down on the kid, and we have a force of tension up on the kid. So you have to remember that this force of tension is split into a force of tension on the x and force of tension on the y, and that there are 2 force of tensions on the y, and they're identical. So let's get rid of that. If we do sum of forces on the x, we know that it's force of tension 1 on the x and force of tension x2, and they equal 0, so they're equal and opposite, but we don't really care much. On the y, they're also 0 because this kid is suspended, and we've got gravity down, force of tension on the y1 up, force of tension on the y2 up. We know that these 2 things are the same. We also know that force of tension on the y1 is really equal to force of tension times, if we look at our angle being here, and there's our side, force of tension times, sine theta 1, and this is force of tension sine theta 2. Well, we know that those are identical, so This is 2 times the force of tension times sine theta. Okay, so having cleaned all that up, we now know that f of g plus that equals 0. So at this point we're ready to do some pretty simple algebra. Okay, so the negative of f of g is going to equal 2 force of tension sine theta. So the negative f of g divided by 2 sine theta equals the force of tension in each cable. So we plug our numbers in there, and the raw answer we get for force of tension is 382.4179, etc. When we account for sig figs having 2, we get a force of tension of 380 newtons. And because it is a vector, you need to say something about direction. That would be 380 newtons along the cable is the easiest way to express that. Okay, that's number 3. So this is 4B number 1, and now we're into net acceleration and forces. So we have a slope, we have a sled, and we have a friend. And our free body diagram would look something like this. So we have a force of gravity going straight down. We have an applied force going up the hill, and that applied force is 1,863 newtons. And we know that this slope makes a 25-degree angle with the horizontal. And we can break our force of gravity up into a force of gravity on the y and a force of gravity on the x. So the y, we don't have normal force here. This is really, again, technically before the point at which we would think of normal force. So we're just going to look at the x-axis, and our sum of forces on the x, we know that this is where our acceleration is occurring, is equal to our mass times our net acceleration. And what we've got there is the force applied, the force up the slope, and the force of gravity on the x, which is pulling you down the slope. So we're now working with this. Ma net is equal to the force applied, and that's going to be a positive number in the end, plus the force of gravity on the x, which is, of course, force of gravity times, because we know that that's also 25 times the sine of theta. And this has to be a negative number in the end. So we'll go one more step, and that's got to be a positive, plus mass gravity sine theta. And that gravity is going to get us our negative where we want it. So mass times net acceleration. So if we divide both sides by mass, we've now solved for acceleration. And at this point, it's just a matter of plugging in numbers. So we get a net acceleration of 22.854114, etc. With 2 sig figs, we get a net acceleration of 23 meters per second squared. And we should say up the slope to give us a vector. Okay, that's number 1 on 4B. It's also number 4 overall. Okay, so on 4B, the second one, we have a box of Christmas cookies suspended by a cable, and the box is being pulled upward. So we have a net acceleration of 1.5 meters per second squared. What we want to know is the force of tension on the cable. So we're going to briefly just acknowledge that the sum of forces on the x is 0. We don't even have any listed forces on the x, so we're now going to disregard it. Now let's look at the y-axis where all the action is. And we know that sum of forces on the y is equal to the mass times the net acceleration, which is also equal to the force of tension plus the force of gravity. And that's an up force, that's a down force. This will be a positive by convention, and that will be a negative by convention. So we can now start working with this. We know that we have Ma net equals force of tension plus, and force of gravity, of course, is mg. What we're interested in is the force of tension, so we can now rearrange to get Ma net minus mg equals force of tension. Of course, don't forget that's going to be a negative number, so we're going to be subtracting a negative, in essence, adding it. We can factor out the mass, and we get mass times A net minus mg, and of course we're actually going to be adding that, but we're subtracting a negative, is equal to the force of tension. That looks like this when we plug some numbers in, 1.50 meters per second squared minus negative 9.81 meters per second squared. That equals F of t. We get 260.13 newtons is equal to the force of tension. With sig figs, and we have 3 sig figs in this problem, tough to get that down to 3 sig figs. You have to do 2.60 times 10 to the second newtons for your force of tension to get 3 sig figs. Okay, moving on to the 4C&D problem. Oh wait, no, we have 2 more on 4B. Okay, so here you're sitting out in the car on a pond, and you get pushed around. We want to know what your net acceleration is. So again, it's just a net force problem, and we've got I'll go ahead and do a little bit of this with the video paused. So we need to look at our axes and list all the forces we have. Okay, so on the x-axis we have force of Grant pushing west, force of Brooke on the x pushing west, and force of Leanne pushing east. I'm not going to put in all the numbers here, but we have to, of course, use our trig functions, and we can see the, whoops, cut that. There's our x, there's our y. So using all of our trig, we're going to, this is force of Leanne times cosine of 25, this is force of Brooke times sine of 15. So I'm just going to sort of do the hurry-up version of this, and our overall x force is 2,561.34, etc. newtons, and that is to the west. We'll do our sum of forces on the y, and we have the force of Ashley, which is north, plus the force of Leanne on the y, which is also north, and that's being countered by the force of Brooke on the y, which is south. So again, just treat sign conventions with standard, sort of a standard grid, and when we plug in all our numbers, we get a sum of forces y of 1,086.496, etc., and that is to the north. So this is actually, if we're using our sign conventions, that's a negative number. This is a positive number. So now we want to make our overall triangle, and we have our negative 2561.34 newtons. We have our 1086, etc. And so our resultant, of course, is going to be something like that. That's the net force. So the net force is equal to the square root of the 1086, etc. squared plus the negative 2561, etc. squared. We get a net force of 278226, etc. And when we use our inverse trig function to figure out that angle theta, theta works out to be 22.9 something degrees, so it's 23 north of west, and of course you can use the complement if you want, but the net force is only part of what we need. What we're really looking for is our net acceleration, and we know that F net equals mass times net acceleration, so if we divide both sides by mass, we get our net acceleration. And at this point we're simply plugging in our net force number there, and we've got the mass of the car, which is 1,275 kilograms. We get a net acceleration of 2.1826, etc. And we have 3 sig figs, 2 sig figs, 3 sig figs. So we end up with a net acceleration of 2.18 meters per second squared at that angle that we found. Okay, we'll pause for a moment. Okay, so this is number 4 on the 4B quiz. This is the Peter Pan problem, and we've got U on a single cable system. We know that we have a force of tension in the cable, and we know that we have a force of gravity down on U. We can do sum of forces on the x equals 0 and then disregard it. And what we're really interested in is sum of forces on the y. That's going to be equal to your mass times your net acceleration. And again, we've got a force up, force of tension, and we've got a force down, force of gravity. So the other thing we know is that ma net is equal to ft. Well, that fg is really mass gravity. So now we can rearrange mass net acceleration minus mass gravity equals ft. So we can factor out an m. We've got a net minus g. That equals ft. We know that overall this is going to be a negative number. So in fact what we're doing is adding gravity to acceleration. We have our 46 kilograms, 3.5 meters per second squared minus, and that's a negative 9.81 meters per second squared, gives us our force of tension. We have a raw answer of 612.26 newtons, and with sig figs we get 610 newtons is equal to the force of tension in that cable. Okay, I'm going to cut the video here, so the 4C and D FIP solutions will be on a separate video. So again, this is the 4A and 4B FIP solutions.